Many of you may have been there on the weekends. Our colleague Jerry Zimmerman from State, Mr. Fries, Dr. Fries, Professor Fries, has entertained and enlightened lots of people all ages with his demonstrations of liquid nitrogen and wonders of that. He is covering himself in snow. And if I could get 10% of that money from you tonight, that would be really nice. Here are kids and teachers at the Science Education Center. Fermilab people, the Lettermans, Marty. On an earlier occasion, we actually arrayed all of them here in front of the stage. Now so many of them are coming in electronic form that it's not so impressive to show the file names. But that's a lot of PhDs that we've helped make, and a PhD is for society for 50 years. So these people are valuable to us, whatever they choose to do. Okay, I want to say some words now about the Tevatron, which was our second great accelerator. It was a dream of Wilson early on that it might be possible to go beyond the original energies. The specifications for the Fermilab machine were to reach 200 billion electron volts, which, as we saw, happened in 1972. He wanted to deliver more and eventually delivered stable running at 400 billion electron volts. That enabled, by the way, the discovery of the Upsilon particle and the B quark by the Letterman group. At the original design energy, that would not have been possible, so the higher energy benefited that. Eventually it was possible in short bursts to go up to 500 billion electron volts, but Wilson wanted to push for higher. To do so required changing technology in two ways. One was to replace the old-fashioned electromagnets in the main ring with superconducting magnets that can give you much higher magnetic fields and therefore bend in a circle particles of much higher energy. And also, because they don't heat up, don't waste electrical power by heating up the copper in the normal magnets. So if you can only make these work, it is a great benefit to building an accelerator. Well, through a lot of hard work by people here at Fermilab and elsewhere, and this goes from the people who invented the superconducting substances, niobium, titanium in this case, the ones who made the strands, the cable, my colleagues here, who discovered how to make a magnet that would withstand the pressures that happen when you excite it to very, very high magnetic fields, learned how to build this machine. And it was a real tour de force on many, many accounts, allowed us to double the energy of the original machine in the same ring. Originally, we reduced the power consumption by about a factor of 3 while doubling the energy, so that was a fantastic step. Here at the top, you see the magnets of the original main ring. On the bottom, you see the magnets of the Tevatron, the superconducting machine. Wilson claimed that he had always intended to build another machine there, and that's why he left the holes in the magnet stands. He might have done it to save material and cost as well, but it was an inspired choice, however it happened. If you're going to build a superconducting machine, you have to keep the superconducting material at very low temperatures, so in our case about 4 degrees above absolute zero, and if you're going to do that, you need a very big refrigerator. So we had, for a time, the largest helium refrigerator in the universe, run by this set of people. It's out there across from the CDF building, now called IARC. So here was the great moment at which the new Tevatron operated and reached the highest energy anybody had attained at that point, 512 billion electron volts. A lot of happiness there, a lot of relief probably as well. More celebrations. So Letterman pouring some substance. Wilson was back for the occasion and was suitably pleased. Four of my colleagues who were particular heroes of this effort: Alan Tolstrup on the right, who was a big driver behind making the magnets, understanding how to make the magnets; Helen Edwards, who was designed and implemented the machine with a big team of people; Rich Orr and Dick Lundy, who were in charge of manufacturing the magnets and other things. They're on the occasion here, they're dressed not for work, but because they were at the White House to receive the National Medal of Technology for their fantastic achievements. Okay, so we're accelerator builders at this laboratory. It is the National Accelerator Laboratory. And accelerators can be used not only to go to the highest energies and to do particle physics research, but for medical applications. And for a number of years, the beam for the LINAC was used, when it wasn't required for other purposes, to make a beam of neutrons that could be used for cancer therapy for soft tissue cancers. So on the right, looking at CAT scans, one of my colleagues who was a leader in this enterprise. On the left, showing off his six-pack abs, or abs of steel, one of our radiation technicians showing how a patient would be arrayed there. So there are a lot of people treated for soft tissue tumors using these techniques. Protons are another way of treating certain cancers, and my colleagues here built a compact proton synchrotron for the Loma Linda Hospital in Southern California, which has now treated many people for things like prostate cancer and other things, and which has given rise to the spread of proton therapy for certain kinds of cancer, including a number of centers in this area modeled on the device that they built. Okay, so what's the Tevatron used for in particle physics? There are two ways of thinking about it. One is to use the beams of higher energy to use extracted beams and to study what happens. I want to give you two examples, both because they took a long time to perfect. It's maybe in the old days, maybe in a high school physics lab, you go into the lab and you get an idea, or you're given an idea and you do the experiment, and it works or doesn't. Often, what we call experiments are institutions that live for a decade or a decade and a half or 2 decades, in which people come together pursuing some initial goals. They learn better and better how to accomplish those. They get new ideas along the way. So this is an experiment to look for the properties of what are called charmed particles, those made of the fourth quark and light quarks. And this was the second major experiment in that sequence. The first experiment had a number of near-death experiences, although it had a number of very good ideas in it and produced some intriguing initial results. But there were two important innovations here. One was to take advantage of a technology then being developed around the